Determine all intervals of concave up or concave down and determine the coordinates of all inflection points, including cliffs, for the function f of x equals x to the 1/3 times x minus 16. The first thing to do is find the domain. F of x equals x to the 1/3 power, a fractional exponent. The denominator of a fractional exponent is the root. It is an odd number here, and the domain of an odd root is all real numbers, times x minus 16, a polynomial, and the domain of a polynomial is also all real numbers. So collectively we have a domain that is all real numbers, or negative infinity to positive infinity. The next thing to do is find all candidate numbers. We will need the second derivative for this. We will start with the first derivative. F of x is the product of two expressions of x here. So the first derivative will require the product rule, at least as written. But we have the option of distributing the x to the 1/3 in to the x minus 16 to eliminate the need for a product rule. Before we do that, we can rewrite the x to the first power in the parentheses as x to the 3/3 power so that it has a common denominator. So when we distribute the x to the 1/3 in, we can add the exponents. X to the 1/3 times x to the 3/3 is x to the 1/3 plus 3/3, or x to the 4/3 power. We have a minus 16 that does not have an x, so when we distribute the x to the 1/3 in, it will just multiply with the negative 16. Each term is now just a power rule for the first derivative. F prime of x equals, the first term is power rule, bring the power down, leave the inside alone, subtract 1 from the power, I will call that 3/3, and then multiplying by the derivative of the inside of each of these powers are just x, the derivative of x is a 1 for the chain rule, so no need to write it. The second term we have a negative 16, we will bring the power 1/3 down, and we will subtract 1 from that power, which again I will call 3/3. The first term is 4/3, x to the 4 minus 3, 1/3 power. The second term we have a minus 16 times a 1/3. We will multiply the numerators. Minus 16 times 1 is minus 16 over the 3. And x to the 1 minus 3, negative 2/3 power. We can take the second derivative directly from here. The first term is a power rule. We have a 4/3. The 1/3 power can move down to multiply with the 4/3. We'll subtract 1 from the power. I will call it 3/3. And then we have a minus 16/3. The second term is also a power rule. Bring the power down. It's a negative 2/3. X to the, subtract 1 from the power. The first term we can multiply the fractions. Multiplying the numerators, 4 times 1 will be a 4. Multiplying the denominators, 3 times 3 will be a 9. X to the 1 minus 3, negative 2/3 power. The second term we can multiply the fractions. Multiplying the numerators, negative 16 times negative 2 is a positive 32. And 3 times 3 multiplying the denominators is a 9. X raised to the minus 2 minus 3 minus 5/3 power. We will want the second derivative written as a single fraction with all powers positive and fully factored. One option is to move these negative powers to the denominator, get a common denominator between it, combine it together, and then factor the result. Another option is to factor it as is. That's usually the quicker and easier version. We have a common factor from the numerator between 4 and 32 of 4. And from the denominator, a 9 and a 9, a common factor of 9. And then we have an x to the negative 2/3 power and an x to the negative 5/3 power. We can factor out the lower of the two powers, which will be the negative 5/3, because it is more negative, making it lower. So x to the negative 5/3 power. Factoring that out, we'll leave behind, starting with the numerator, we're going to factor out a 4. That'll turn that into a 1 and that into an 8. In the denominator, factoring out a 9, this will become a 1, this will become a 1. And now factoring out the x to the minus 5/3 power, factoring is division, and division is subtraction of exponents, so we will be subtracting a negative 5/3. Subtracting a negative 5/3 is equivalent to adding a 5/3. So we will add a 5/3 to this power. 5/3 minus 2/3 is 3/3 or 1. And all of this will become a 1 power. So we'll have x to the 1. Adding 5/3 to this power, 5/3 minus 5/3 is 0. We have x to the 0 power, and x to the 0 is a 1. So we will have an 8 times 1, or just an 8. So altogether we have a 1x plus 8. One x can be written as x and then plus 8. We want all powers to be positive so that x to the negative 5/3 can move to the denominator to become a positive 5/3. The 4 will stay in the numerator. The x plus 8 will stay in the numerator. I'll put it in parentheses instead of square brackets now. In the denominator, there's a 9 already down there from the 4/9, and the x can move to the denominator to become a positive 5/3 power. We now have the second derivative written as a single fraction. Every power is positive, and it is fully factored. We can set the numerator equal to 0 and the denominator equal to 0 and solve for all x's, starting with the numerator. 4 times x plus 8 equals 0. We can divide both sides by 4. X plus 8 equals 0, and subtract 8 from both sides. X equals negative 8. Now working with the denominator, 9x to the 5/3 equals 0. We can divide both sides by 9. X to the 5/3, 0 divided by 9 is still 0. And now raise both sides to the reciprocal of 5/3, which is 3/5 power. We want it to be the reciprocal of 5/3 because when you raise and raise again, we multiply the exponents. 5/3 times 3/5, multiplying the numerators, 5 times 3 is 15. Multiplying the denominators, 3 times 5 is also 15. It'll be 15 over 15, which is a 1. So we have x to the first power, or just x, equals, and 0 raised to any non-zero positive number is 0. We now check to see which of these are in the domain. The domain is all real numbers. X equals negative 8 is a real number. X equals 0 is also a real number. Each of these are candidate numbers. We can now draw a domain line, a line representing the domain. It has no left end because it starts at negative infinity. It has no right end because it ends at positive infinity. We can put all candidate numbers on here in order. We have a negative 8, and we have a 0. This splits the domain interval up into 3 separate intervals. We can pick a test value in each of these intervals. The first interval is negative infinity to negative 8. We can pick negative 10 in there. The next interval is negative 8 to 0. We can pick negative 5 in there. And the next interval is 0 to positive infinity. We can pick positive 10 in there. We can now test the concavity in each of these intervals By plugging the test value into the second derivative, we don't care about the value of the second derivative, we just care whether it is positive or negative. So the best place to plug in will be the fully factored version of it, which is the version there. Something to know about this: in the denominator, x to the 5/3 power. 5/3 power means the root is the 3. It'll be a cubed root. And the power, the exponent, is 5. Both of them are odd numbers. An odd root of a negative number is still negative. And an odd power of a negative number is still negative. So if we put a negative number in for x in the denominator, it will be a negative number that comes out of it. If you put a positive number in there, a positive number raised to the 5/3 will still be positive. Starting with the -10, plugging it in the numerator, it'll be -10 plus 8, which is a negative number, times the 4 will still be negative. In the denominator, a negative number raised to the 5/3 power will be negative, because they're both odd, and then times the 9 will still be negative. So we have a negative over a negative, which is a positive second derivative, and that corresponds to concave up. We can now plug in -5 into the fully factored version of the second derivative. In the numerator, -5 plus 8 is a positive number, times the 4 is still positive. In the denominator, a negative number to a 5/3, an odd root and an odd power, will be a negative. And then times the 9 will still be negative. We have a positive over a negative, which is negative. We have a negative second derivative, which corresponds to concave down. Now plugging a positive 10 in the numerator, 10 plus 18 is positive, times the 4 will still be positive. In the denominator, a positive 10 to the 5/3 will be positive, times the 9 will still be positive. We have a positive over a positive. That is a positive second derivative, which corresponds to concave up. So we have concave up happening on the interval -infinity up to -8. Union, because it's happening again, on the interval 0 to +infinity. We have concave down happening on the interval -8 to 0. Right at the candidate number of x equals -8, we have the concavity changing from concave up to concave down. That means that x equals -8 is an inflection point. It has an x-coordinate of -8, and it has a corresponding y-coordinate, which can be found by plugging the -8 back into the original function. So y equals f of -8, which is -8 to the 1/3 power times -8 minus 16. 1/3 power means cubed root and then first power, so it'll be the cubed root of -8. And then -8 minus 16 is a -24. Cubed root of -8, cubed root of a negative number is negative, cubed root of 8 is a 2. We have a -2 times a -24. Negative times negative is positive. 2 times 24 is 48. So we have a corresponding y-coordinate of 48. Right at the candidate number of x equals 0, we have the concavity again changing from concave down to concave up. So x equals 0 will also be an inflection point. It has a corresponding y-coordinate that can be found by plugging the x-coordinate of 0 back into the original function. So y equals f of 0. Which will be 0 to the 1/3 power times 0 minus 16. 0 raised to any non-zero positive number will be 0. 0 minus 16 is negative 16. 0 times any number is equal to 0. So we have a corresponding y-coordinate of 0. One thing to notice about this inflection point occurring at 0, 0, the x equals 0 candidate number back up here came from the denominator. And if there is a candidate number from the denominator and it turns out to be an inflection point, it's an inflection point by being a cliff. So that right at the 0, 0, which is the origin, we have a cliff. It's changing from concave down to concave up. So that means it'll be concave down and then becoming concave up. So it'll be a cliff shape like this, where the origin will be right there. That'll be the shape it takes on for the graph. So we have 2 intervals of concave up, 1 interval of concave down, and 2 inflection points, one at negative 8, 48, and another one that turns out to be a cliff at 0, 0, or the origin.